This is again a video on information coding. So this is basically information coding for the purposes of error detection and correction. Now, the objective behind the coding of information for the purposes of error detection and correction is to code the information in such a fashion that it must be possible to detect whether an error has occurred during the transmission of the code, and indeed if an error has occurred, then exactly where in the code has the error occurred and what is the exact error that has occurred so that it might be appropriately corrected. So basically we saw earlier, generally for error detection and correction, the general problem definition involves possible changes in the length of the information. I will not assume that. As I said earlier, the only errors that I am considering are, I am assuming that if certain L bits are transmitted from one end, exactly L bits are received, and the only possible errors I am looking at are possible errors in the value or changes in the value of these L bits. Okay. So basically here we have L dash bits here. We wish to code this as L bits. Now what happens if you transmit these L bits across and there are changes in this value, then you must be able to detect whether change has occurred, if it has occurred, where exactly in the entire code has it occurred, and what is the exact error that has occurred so that it can be corrected. A simple technique which is really effective, which should be really effective, is to simply code the information or the message as a permutation. Meaning, if you are given an information of length 2 power L dash, we simply code it, determine L such that L log L equal to 2 power L dash. In other words, L dash is, we determine L such that L times Lg is binary log L is equal to L dash. Now we simply code the L dash bits of information as a permutation of length L, 0 to L, L minus 1. Some permutation of that is what represents this information. Okay? So what happens now is, if you transmit that permutation across and you know what the value of log L is, or log L you can immediately know. So it means all of the L digits, if the information, the code is regarded in base log L, then all L values from 0 to L minus 1 must occur there. Where repetitions occur, that is where error has occurred. Now the only possible errors that will slip through this, which is very, very rare, but nevertheless we have to account for it if we are to make some kind of a slightly foolproof as possible, is to account for instance here, let's say I have here 0, 1, 2, 3, 4 and 5. This is the original value. Now we know that we can use the permutation notation itself. Here. So therefore, if we have here a permutation 0, 1, 2, 3, 4, 5, then we can have here 0, 1, 2, 3, 4, 5. Okay. Let's assume some L dash bits has been coded as this permutation 510324. Length here is L is 6, sorry. So the digits from 0 to 5 must all occur in the code. Okay, where repetitions occur, those digits which repeat are the ones must be replaced by the digits which are, or numbers which are missing. So in order to perform that replacement, we can either use some kind of a checksum kind of a thing you can try to do. For instance, summation wi/di, if we do, if wi are all prime numbers larger than the length of the size of the length, then the size of the alphabet or the size of the digit primes, then what happens is this will never happen. The collision probability will be very small. It will detect most errors here, but errors which are cycles or transpositions or permutations of this itself, it will not detect. Meaning, instead of, if this permutation is transmitted, then some other permutation is received, then correcting that permutation using this might be possible. It will be very tedious or cumbersome. You might have to go through a very large number of permutations to do so. The other alternative is to compactly code the permutation itself. That is, in this case, so we make use of the facts that we know about permutations, right? Every permutation can be expressed as a product of cycles, and then here 1 is a identity. So here 0 goes to 5, 5 goes to 4. So we may write this as 0, 5, 4, 2, and then again 3, 3. There are two digits which are identical. Okay. Identity ones. Here now what you will notice here is that these are all cycles here. If you take these elements, the cycles of these elements, they are all equal cycles. Okay, but you can also notice that for every cycle, including for a transposition, here 1 is exchanged with 1, 1 is again exchanged with 1. For other than identity ones, if you take this here, you take the sum of these differences here, it will always add up to 0. You have 5 minus 0 plus 4 minus 5 plus 2 minus 4 plus 0 minus 2 is equal to 5 plus minus 1 minus 2 minus 2 is equal to 0. So for this permutation that we transmit across, we make a legend or some kind of that consists of, for that information that is coded, what are all the lengths of cycles, how many different lengths are there of the cycles, and for each length what is one of the elements in the cycle, and what is its positive sum. Okay, this information you can, again, that would constitute the legend. This permutation itself is the information itself, and this information would constitute the legend. This legend, what you can do is, either for singleton sets and identity sets, you could try to compact it, or you could try to, or the other way, the right way would be, for the legend alone, you again perform an error detection and correction, meaning you again code the legend as a permutation. and for that code again you will generate another legend which you can again code as a permutation. So we can do it that way. So recursively code the information. Another important thing to note is that any permutation is nothing but a sorting algorithm. Any algorithm for or more appropriately, every sorting algorithm is an algorithm for generating a permutation, that is all. Okay? So here instead of 0, 1, 2, 3 you will have some set of numbers with some differences between in an ordered set, which you must every sorting algorithm must permute the elements of the set to be sorted. So every sorting algorithm is a permutation algorithm. So another way of looking at this is to try to code a sorting algorithm compactly here for that particular permutation. The permutation that you use for this permutation, you can try and sort it to 0, 1, 2, 3, 4, 5 by a very, very efficient method which you can compactly try and code that sorting algorithms method used to generate this to this. So when this is transmitted and you apply that sorting coded information, you should be able to get this. But if you do not, then you know what transmission errors have occurred there, so you are able to make those transpositions to get that. That means the algorithms for sorting. So with that in mind, we can come up with many ones, and there are already a lot of sorting algorithms which are good. You can also come up with other ones. I was just looking at it and I came up with one of these. So I'll look at it later in a separate video for sort. So from this we can glean that algorithms for information coding are almost the same, if not exactly identical to the algorithm the data structure or information structure algorithms for searching and sorting, right? They are more or less the same. For the case of error detection and correction also, this is one way of doing it, and since a permutation algorithm or a sorting algorithm is nothing but a permutation generation algorithm and they are more or less identical, so right? So the theory of data structures or information structures and the theory of information coding are very, very much akin to each other, are very, very closely related and very, very closely knit together, closely woven together. Each of those algorithms can serve for the searching and sorting algorithms are used for information coding as well.